So now, question 9. What is a buffer solution? So, buffer solutions, if I can try a different color, resist changes in pH. Okay, how? Because a buffer solution has a mixture of its acid and conjugate base. So the way this breaks down here is that if you added more acid, the conjugate base in it would resist that change until there was no more conjugate base left, and then it's no longer a buffer. Same thing, if you added a base, the acid would keep it around that pH until there was no more acid left, and then it would no longer be a buffer solution. In fact, based on what I described, actually, you should be familiar with these, the titration curves. Actually, when you're trying to titrate a weak base with a strong acid, or vice versa, a strong base, you're trying to titrate a weak acid with a strong base. But these curves typically look like that. Okay, so right here, this is where the buffering, I guess, ends, if you think about it, because here's like where the buffering is really taking work. You see how the pH is trying to increase, but as you're adding base, it's resisting it until we get to the point where there's no more of the, I guess, acid, and then all that's left is a conjugate base, and then you notice it skyrockets, breaks out of that buffer. So this is what it's looking like in terms of like the titration curve. But what you have to remember is that the buffer solutions only work, okay, this is an important part, with weak acids or bases. Now you're probably wondering why that's the case. So the issue with strong acids is that they dissociate completely, and strong bases. So let's say I put in HCl in a solution. Every part of it will separate to H and Cl. That's guaranteed. Now, if I put in NaOH, same thing would happen, where it just breaks down to sodium and OH minus. So the reason why this is important is because this right here doesn't really count as an acid and its conjugate base. It's just a complete dissociation of it. So that's what would happen there. But if we had something like CH, this is a different color actually, CH3COOH, this right here is also known as acetic acid. Okay, this would not thoroughly, because it's a weak acid, so does not completely dissociate, but there will be CH3COO minus and H plus. Now the reason why this is different is because in the HCl situation, right, it dissociates completely. There's now no quote-unquote balance of HCl in the solution. It's all just H plus, which just goes 1-to-1 ratio. You know, you add some base, it reacts with the hydrogen, and you see that with strong base and strong acid, it'll look like that, a straight line, because it's directly related. The amount of base you add will cancel the amount of acid that I have, and it'll just be a linear relationship. But with this, because you have some of acetic acid and its conjugate base floating around in the same solution, that is when you have a buffer solution. And it's important to develop a strong buffer solution that you add some amounts of both the acid and the conjugate base. You don't just put the acid and then think it will dissociate to form the conjugate base. So with all that being said, a buffer solution, just to recap, it's never resist change in pH. Okay, it only works with weak acids or weak bases. Okay, and you need, well, actually let me write here the last part, you need conjugate. Okay, if you just poured in acetic acid, technically that would be a buffer solution because it does produce some of its conjugate base, but it would not be a very good buffer solution because there would be quite little of its conjugate base. You would need acetic acid in one, and then actually CH3COO minus in another, and mix together to get a more of a proper buffer solution. So let's see here what they say. Buffer solution is a solution that can resist drastic changes in pH upon the addition of acidic or basic components. So let's see. Just gotta drink some water. Should contain a weak conjugate acid base pair, which means that it has to be its weak acid and its conjugate base. Yep. Acetic acid, they do mention that. Actually, that is a good point. The way they added the conjugate base is that you won't really see just CH3COO minus like on the label. It needs to be actually paired with something, and usually just pair with a salt. So this is its conjugate base because it's sodium with the CH3COO. And you know, with sodium, usually things just dissociate, and you just get the sodium plus, and then bam, your conjugate base is free to roam around. CH3COO minus. So that is what's happening there. Ammonia is actually another example. It's a weak base, and then you can add interesting, ammonium hydroxide. I would think that that one would, I'd actually go probably maybe like NH4 Cl maybe, but that would just be me. But point being is that exactly, just make sure that you have the acid and its conjugate base, or vice versa, to form a buffer solution. It cannot be a strong acid or a strong base, or else it dissociates completely, and that doesn't work. It becomes a 1-to-1 ratio. And the point of the buffer solution is that it resists changes in pH. This is correct. All right, and now for the final question for the evening, at least.